You know, people love to talk about aliens. They love to imagine these advanced civilizations out there, cruising around the galaxy in fantastic spaceships, visiting planets, maybe even coming here to Earth. And I understand why. It's exciting. It captures the imagination. But let me tell you something that might disappoint you. If you really sit down and work through the physics, the actual numbers, the real constraints that nature puts on travel through space, you start to realize something pretty profound. The aliens, if they exist, are probably never going to get here. And we're probably never going to get to them either. Now, before you think I'm being pessimistic or that I don't believe in the possibility of life elsewhere, let me be clear. I think it's almost certain that life exists somewhere else in the universe. The universe is so enormous, so filled with stars and planets, that it would be remarkably strange if Earth were the only place where chemistry got complicated enough to produce living things. The real question isn't whether they're out there. The question is whether we'll ever meet them, whether they'll ever show up here, whether any kind of meaningful contact is physically possible given the laws of nature as we understand them. And when you look at those laws carefully, when you actually do the arithmetic, you find out that the universe is set up in a way that makes interstellar travel almost impossibly difficult. Not impossible in principle, mind you, but so difficult, so energy intensive, so time consuming that it might as well be impossible for any civilization that has to worry about resources and engineering and the basic limits that physics imposes on matter and energy. Let's start with the most basic problem, the one that everybody sort of knows about but doesn't really appreciate until you see the numbers written down. The distances between stars are absolutely stupendously, mind-bogglingly huge. When I say huge, I don't mean like the distance from New York to California. I don't even mean like the distance from the Earth to the Moon. I mean distances so large that our usual units of measurement become completely useless. The nearest star to us, Proxima Centauri, is about 4.2 light years away. Now, a light year is the distance that light travels in 1 year. And light is fast. Light goes around the Earth about 7 times in 1 second. In a year, light travels about 9.5 trillion kilometers, so Proxima Centauri is about 40 trillion kilometers away. That's 40 with 12 zeros after it. To put that in perspective, the fastest spacecraft we've ever built, the Voyager probes that we sent out in the 70s, are traveling at about 17 kilometers per second relative to the Sun. That sounds fast, and it is fast by human standards. But at that speed, it would take those probes about 70,000 years to reach Proxima Centauri. 70,000 years. That's longer than all of recorded human history. That's longer than humans have been doing agriculture. And that's just to get to the very nearest star, which, by the way, probably doesn't have any interesting planets around it. If you want to visit a star system that might actually have planets where life could exist, you're probably looking at distances more like 10 or 20 or 50 light years. And now your travel times start getting into hundreds of thousands of years, maybe millions of years, even at the speeds our best current technology can manage. So, right away you see the problem. If some alien civilization wanted to send a spacecraft to visit us, even if they're only 10 light years away, even if they have technology that's somewhat better than ours, they're looking at travel times that are enormously long compared to the lifetime of any individual organism, probably long compared to the lifetime of any civilization. But okay, you might say, maybe they just build really big ships, generation ships, where many generations live and die during the journey. Or maybe they put themselves in suspended animation, freeze themselves, or slow down their metabolism somehow. These are ideas that show up in science fiction all the time, and they're not completely crazy. In principle, you could imagine doing something like that. But now let's talk about the energy problem, because this is where things get really nasty. To accelerate a spacecraft to a significant fraction of the speed of light, which is what you'd need to do to make the travel times reasonable, requires an absolutely enormous amount of energy. Let me give you a concrete example. Suppose you want to send a spacecraft to a nearby star, and you want it to get there in a reasonable time, say 50 years instead of 50,000 years. To do that, you need to accelerate the spacecraft to maybe 10% of the speed of light. That's about 30,000 kilometers per second. Now suppose your spacecraft has a mass of just 1,000 kilograms, which is pretty small, smaller than most cars. To accelerate that spacecraft to 10% of the speed of light, you need to give it kinetic energy. The formula for kinetic energy is 1/2 times mass times velocity squared. When you plug in the numbers, you find that you need about 4.5 times 10 to the 17th joules of energy. That's 450,000 trillion joules. To put that in perspective, that's roughly the total energy output of the entire United States for about a month, just to get one small spacecraft up to speed. And that's not counting the energy you'd need to slow it down when you get there, which is another huge amount. And it's not counting the energy you'd need to carry along as fuel if you want to do anything when you arrive, like orbit the destination planet or send back information or explore or return home. And here's the kicker. Where does that energy come from? If you're using conventional rockets, Chemical rockets like we use to launch things into space today, you're out of luck. The energy density of chemical fuels is just way too low. You'd need a fuel tank that's vastly larger than the spacecraft itself, so large that it becomes completely impractical. You might think, okay, well, what about nuclear energy? Nuclear energy has much higher energy density than chemical energy. If you could build a spacecraft powered by nuclear fusion or nuclear fission, maybe you could do better. And yes, that's true, nuclear energy helps, but even with nuclear energy, the numbers are still brutally difficult. There's a fundamental equation in rocketry called the Tsiolkovsky rocket equation. It tells you how much fuel you need to achieve a given change in velocity, and it depends on the exhaust velocity of your rocket, which is related to how much energy you can extract from your fuel. Even with the best possible rocket exhaust velocities you could imagine getting from nuclear reactions, you still end up needing enormous mass ratios, meaning the mass of fuel compared to the mass of the payload. For example, if you want to reach 10% of light speed using a nuclear fusion rocket with an exhaust velocity of maybe 3% of light speed, which is extremely optimistic, you'd need a mass ratio of about 30-to-1. That means for every kilogram of spacecraft, you need 30 kilograms of fuel. And remember, that's just to speed up. If you want to slow down at the destination, you need even more fuel, which you have to accelerate along with everything else, which means you need even more fuel to accelerate that fuel, and so on. The whole thing spirals out of control very quickly. Now, some people propose using things like antimatter as fuel. Antimatter annihilates completely with matter, converting all of the mass into energy according to Einstein's famous equation, E equals mc squared. That's the highest possible energy density you can get. But even if you could somehow manufacture antimatter in large quantities, which we absolutely cannot do with current technology, and even if you could store it safely without it annihilating with the walls of your container, which is extraordinarily difficult, you're still limited by the rocket equation. You still need enormous amounts of reaction mass to throw out the back of your rocket to generate thrust. There are some clever ideas to get around this. One idea is the laser sail, or the light sail. You put a big reflective sail on your spacecraft, and you shine an enormously powerful laser at it from your home planet. The light from the laser pushes on the sail and accelerates the spacecraft. The nice thing about this is that you don't have to carry your fuel with you. The energy source stays at home, and you just use the light to push yourself along. But even this has problems. First, you need an absolutely colossal laser, something that puts out maybe 100 gigawatts of power or more, sustained for years. That's roughly the total power output of 100 large nuclear power plants, and you need to focus that beam incredibly precisely over distances of light years. Any spreading of the beam means most of your energy misses the sail and gets wasted. Second, the sail itself has to be enormous and incredibly thin and light, and it has to be able to withstand the intense heat from the laser without melting or tearing. We're talking about engineering challenges that are far beyond anything we can currently do. And third, even if you solve all those problems, you can only accelerate with this method. You can't slow down because the laser is back at your home planet behind you, so you'd zip past your destination star at 10% of light speed with no way to stop. Unless maybe the aliens at the destination have conveniently built another enormous laser to slow you down, which seems like a lot to assume. There's another idea called the Bussard ramjet, where you scoop up interstellar hydrogen as you travel and use it as fuel for fusion reactions. The advantage is that you don't have to carry all your fuel with you. You just gather it along the way. But the interstellar medium is incredibly sparse. There's only about one hydrogen atom per cubic centimeter in most of space. To gather enough fuel, you'd need an absolutely gigantic scoop, kilometers across, and the drag from plowing through even that tenuous medium at high speeds would be significant. And you'd need a fusion reactor that can burn hydrogen, the simplest and hardest to fuse isotope, which we can't even do on Earth yet, let alone in a compact spacecraft. So every method you look at, every clever idea people have come up with, runs into brutal physical and engineering constraints. And these aren't just technological problems that we might solve with better engineering. These are fundamental limits imposed by the laws of physics, by the speed of light, by the conservation of energy, by the rocket equation. Now, you might say, well, what about something exotic? What about wormholes or warp drives or some kind of faster-than-light travel that we just haven't discovered yet? And here's where I have to be really careful, because I don't want to say that something is absolutely impossible. Physics has surprised us before. But I can say this, based on everything we currently understand about the universe, based on general relativity and quantum mechanics and all the experiments we've done, there's no hint, no evidence, no theoretical foundation for any kind of faster-than-light travel that doesn't violate fundamental principles. Wormholes, for instance, are solutions to Einstein's equations, and in principle they could connect two distant points in space. But to keep a wormhole open, to make it stable enough to travel through, you'd need something called exotic matter, matter with negative energy density. We've never seen anything like that. We don't know if it exists, and even if it does exist, we have no idea how to make it or manipulate it in the quantities you'd need. Warp drives, like the Alcubierre drive that gets talked about sometimes, have a similar problem. The Alcubierre drive is a theoretical solution where you compress space in front of your ship and expand it behind you. So you're not actually moving through space faster than light, you're moving space itself. But again, it requires exotic matter with negative energy density, and the amount of energy involved is estimated to be enormous, like the mass energy of an entire planet or more. It's not clear that it's physically possible at all, and even if it is, it's so far beyond anything we could engineer that it might as well be magic. So when people talk about aliens zipping around the galaxy visiting different star systems, I think they're not appreciating just how hard this is. They're imagining that advanced technology can just solve these problems, that if a civilization is 1,000 years or 1,000,000 years more advanced than us, they can do things that seem impossible to us. But that's not how physics works. Physics doesn't care how advanced you are. The speed of light is the speed of light. The energy requirements are the energy requirements. You can't just technology your way out of fundamental physical constraints. And there's another aspect to this that people often overlook, which is the question of motivation. Even if a civilization could build an interstellar spacecraft, even if they could somehow solve all these energy and time and engineering problems, why would they? What's the point? Think about it from their perspective. If they're curious about other star systems, they can learn an enormous amount just by building big telescopes and observing from home. With a large enough telescope, you can analyze the atmospheres of planets around other stars, look for chemical signatures of life, study the geology and weather patterns, all from light years away. You can send radio signals or laser signals to try to communicate. You can learn a lot without ever leaving your home system. And if you do want to explore physically, it probably makes more sense to send robotic probes, not living beings. Robots don't need food or water or air. They don't mind spending thousands of years in transit. They can be much smaller and lighter, which reduces the energy requirements. They can tolerate radiation and vacuum in extreme temperatures. They're just much more practical for space travel. But even robot probes run into these same energy and distance problems. And once you send them out, you have to wait an enormously long time for results. If you send a probe to a star 10 light years away, and it takes 1,000 years to get there, and then it sends a signal back, which takes another 10 years to reach you, you're looking at more than 1,000 years between launching the mission and getting any information back. That's longer than most human civilizations have existed. It's hard to sustain that kind of long-term thinking. And here's another thing. The galaxy is really, really big. There are something like 200 billion stars in the Milky Way. Even if you could visit nearby stars, even if you had the energy and the technology, you're never going to visit more than a tiny, tiny fraction of them. The galaxy is just too vast. So any civilization that tries to explore physically is going to run up against this wall of distance and energy and time. Now there's a famous question called the Fermi paradox. Enrico Fermi, who was a brilliant physicist, supposedly asked, if the galaxy is so big and so old, and if intelligent life can arise, then where is everybody? Why haven't we seen any evidence of aliens? Why haven't they visited us? And there are lots of proposed answers to this paradox. Maybe life is incredibly rare. Maybe intelligent life is even rarer. Maybe civilizations tend to destroy themselves before they become spacefaring. Maybe they're out there, but they're hiding, or they're not interested in us, or they communicate in ways we don't recognize. But I think one of the most straightforward answers is just that interstellar travel is too hard. The distances are too great. The energy requirements are too high. The time scales are too long. It's not that it's impossible in principle. It's that it's impractical, even for a very advanced civilization. So they stay home, or they send out radio signals, or they explore their own solar system, but they don't zip around the galaxy visiting other star systems. And the same logic applies to us. We're not going to visit the aliens either, not with any technology we can currently imagine. We might send out radio signals and hope someone hears them. We might launch a few robotic probes to nearby stars over the next few centuries if we can solve some really hard engineering problems. But we're not sending people. We're not building generation ships or warp drives. It's just too hard. Does this mean we're alone? No, not at all. I think the universe is probably full of life. It might even be full of intelligent technological civilizations. But those civilizations are stuck in their own little neighborhoods, just like we're stuck in ours. We're all islands, separated by vast oceans of space that are just too big to cross. And there's something kind of beautiful about that in a way. It means that whatever life arises in the universe, it develops on its own, in isolation, following its own path. We're not going to be invaded or rescued or enlightened by some advanced alien species. We're on our own. We have to figure things out for ourselves. And maybe that's how it should be. The universe is a big place, but the laws of physics are the same everywhere, and those laws impose limits. They make some things easy and other things hard, and other things essentially impossible. Interstellar travel falls into that last category, not because of some temporary technological limitation, but because of the fundamental structure of space and time and energy. So when I hear people talking about UFOs or ancient astronauts or aliens visiting Earth, I'm skeptical. Not because I don't believe in aliens, but because I understand the physics. I know what it would take to get here from another star, and it's just not plausible. The universe doesn't make it easy to travel between the stars. It puts up barriers, enormous barriers of distance and energy and time. And those barriers aren't going to come down just because we wish they would, or because we write science fiction stories about starships and warp drives. Physics is what it is, nature is what it is. And we have to accept that and work within those constraints. That doesn't mean we should give up on exploring or searching or wondering. We should absolutely keep building better telescopes, keep listening for signals, keep studying the universe. We should keep pushing the boundaries of what's possible with our technology. But we should do it with our eyes open, understanding the real challenges, not fooling ourselves with fantasies about easy interstellar travel. Because the truth is more interesting than the fantasy. The truth is that we live in a universe that's vast and ancient and full of mystery, but also a universe with rules, with structure, with limits. And understanding those limits, really understanding them, is part of what it means to understand the universe. It's part of what it means to do science. So the aliens, if they exist, are out there somewhere, living their lives, building their civilizations, looking up at their own night skies and wondering the same things we wonder. But they're not coming here, and we're not going there. We're separated by distances that are just too great for any physical visit to make sense. And maybe that's okay. Maybe it's enough to know that we're probably not alone, even if we can never meet. Maybe it's enough to keep searching, keep listening, keep trying to understand our place in this enormous cosmos. Because that search, that attempt to understand, is what makes us human. It's what drives science forward, and it's what gives meaning to our brief moment of existence in this vast, indifferent, but utterly fascinating universe.